Welcome back, students. So this is part 2 of this video where we are talking about the multiple choice questions of grade 8 advanced science. In our previous video, we had covered questions till all this. In the previous video, we have covered the questions from here for the lesson still composition of matter. So now we'll move further. And we'll talk about the questions which are in the other lessons from composition of matter. So you can go through the first video and there you'll find the other questions, multiple choice questions from different lessons. So now we come to the next module, that is, and we are talking about the lesson composition of matter, page 382 and 383. So here the questions which you're going to talk about is classify milk and muddy water as the colloids and suspensions. So you should know about colloids, suspensions, and then you have to talk about river water. If it is a suspension, it is carrying soil and sediment. If river water slows or sits undisturbed, so we're going to talk about that. So firstly, we should know what is suspension and colloid. You know that we have mixtures. Mixtures can be either homogeneous or heterogeneous, right? Homogeneous or heterogeneous. Now, what is a homogeneous mixture? Homogeneous mixture is a mixture in which the components are uniformly mixed. They are mixed uniformly, and the particles are so small that you cannot separate them. That's a homogeneous mixture. We also call them solutions. Soft drinks, they are solutions. Heterogeneous mixture is a mixture in which the particles are not uniformly mixed. The substances are not uniformly mixed. So mixtures can be two types. Heterogeneous mixtures can be of two types. They can be suspensions or colloids. So in this question, they are talking about suspension and colloids. So what you should know what is a suspension and what is a colloid. A suspension, both are heterogeneous mixtures. A suspension is a heterogeneous mixture which is made up of a liquid and solid particles that settle. If you leave them undisturbed for some time, they will settle down. Like if you have an oil and vinegar in salad dressing, you leave the dressing, you will see that the particles is settle down. The seasoning particles in the liquid will settle to the bottom of the container if allowed to sit undisturbed. So if you want to, you have some medicines, also suspensions, which you have to shake before you give it to especially for the children. So they are suspensions. So mainly suspension settles down, colloids don't settle down. This river deltas are large-scale examples of how particles in a suspension settle. So in a river delta, there are particles they behave like a suspension. So when it slows down, the particles, they settle. Rivers flow swiftly through narrow channels. They take up the soil and sediment, and as the river becomes wider, it starts flowing slowly. When it flows slowly, the suspended particles, they settle down. So that is how it behaves as a suspension. Then what are colloids? Colloids are like milk is an example of a colloid. It's also a heterogeneous mixture. It contains water, fat, and proteins in different proportions. But like suspension, though it is heterogeneous mixture, the components will not settle. Even if you leave milk for a long time outside, you don't see that the particles settle, right? So it does not settle. Colloid is a heterogeneous mixture with particles that never settle. Paint is an example of a colloid. Gases and solids can contain colloidal particles too, like fog. Fog, which we see during the winter time especially, if you will see, if you're driving through fog, you can see the light going through, you can see the particles. So this fog is an example of a colloid. Smoke also contains solids suspended in it. That's an example of colloid. So colloid containing suspension water droplets scatters the light and produces, that's why we can see the light of the vehicle's headlights. You can see the rays of the sunlight coming through these. This is again a forest fog. So these are colloids. Milk is a colloid because it consists of tiny fat droplets dispersed evenly throughout water. They're small enough that they do not settle. Even you cannot separate them by filtration. They scatter light. Now, this is a way how we can identify a colloid. How can we identify a colloid from a solution? Suspension you can identify. You leave it for some time, suspension, it will settle down. Colloid will not settle down. In solution also, it will not settle down. How will we identify then if it's a colloid or a solution? By a property which is called Tyndall effect. And this is a property of colloids. If you will see here, this is a colloid and this is a suspension. Here you can see the light ray passing. Here you cannot see. So this is the difference. In solutions, you cannot see the path of the light going, but in a colloid you can see. So this is how we can identify colloid. This is Tyndall effect. Let's come back to our muddy water is suspension because it contains large soil or clay particles mixed in water. They are large enough to eventually settle at the bottom when they are left undisturbed and can be separated by filtration. We can separate them by the process of filtration. Colloids cannot be separated by filtration, but suspensions can be separated. How can we identify? By its appearance, fog appears white because its particles are large enough to scatter light. But sometimes it is not so obvious that a liquid is a colloid. Colloids can look like solutions. Sometimes, see, fog you can note, but here you cannot make out which one is because they look similar. We cannot see the particles. How can we find out which one is colloid, which one is solution? We pass a beam of light through it. When a beam of light is passed through it, it is invisible as it passes through a solution, but can be seen as it passes through a colloid. Here you can see it, but here you cannot. This occurs because the particles in the colloid are large enough to scatter light. Here the particles are bigger than this, so they can scatter light, but those in the solution are not. The scattering of light beam as it passes through a colloid is called the Tyndall effect. This is how to identify the colloid. A soft drink can be homogeneous and heterogeneous. As carbon dioxide fizzes out of the soft drink, it is heterogeneous. Here it is heterogeneous. And the resulting flat soft drink is homogeneous. Here it is homogeneous. Why? Soft drinks contain water, sugar, flavoring, coloring, and carbon dioxide gas. A soft drink in a sealed bottle, if it is sealed, you cannot see the gas and all. It's a homogeneous mixture. It is uniformly mixed and cannot be seen with. Due to the interaction between particles, mixture will never settle to the bottom of the container. So this is a homogeneous mixture. Next question is again from properties of matter. 385 and 86. Describe how you could use physical properties to separate sand from sugar. How we can separate sand from sugar. You're given a mixture of salt and sand. Sand and sugar, salt and sand. How can you separate them? What can you do? You know how we can say we use physical properties for separating mixtures. Supposing you have salt and sand, what we do first, we dissolve it in water. We'll dissolve it. Salt will dissolve in water, but sand will not. Now you filter it. When you filter it, sand will be left on the filter paper and salt will pass through. The water which we get has salt. So we will evaporate it, heat salt solution, and we'll get back salt crystals. And so this is how we separate sand and salt. Sand and salt are successfully separated using filtration and evaporation. So first dissolve, then filter, and then evaporate. So we use physical properties to separate mixture. Removing the seeds from a watermelon can be done easily based on the physical properties of the seeds compared to the rest of the fruit. In the fruit, you can easily make out where are the seeds, you can remove it. Here there's a mixture of sesame seeds and sunflower seeds. You know, sunflower seeds are bigger than sesame seeds. You can identify the two kinds of seed by the difference in their color, shape, and also their size. So if you sift it, the mixture, you can quickly separate the sesame. Take a sift with the size where the sesame goes down and the sunflower is left on the top because of the size difference. Now here there's a mixture of iron filings and sand. So if you have iron filings, a powder of iron, small pieces, and sand, you bring a magnet, iron is attracted to the magnet, you can separate iron from it. This is an example of physical property. Magnetic attraction can be used to separate substances. Similar method is used to separate iron from aluminium and other. Like when we have to do recycling and we want to separate aluminium and iron, we take big magnets, strong magnets in the scrap yards, landfills, they remove iron. And this is how we can conserve our natural resource. Next, again from Properties of Matter, student book 391. What is happening during a chemical reaction in a closed system? Closed system is that energy is not going out or anything. Nothing is going out of the system. Everything is inside it. Here you see this figure, the reaction between sodium bicarbonate. Here you have sodium bicarbonate and hydrochloric acid. This is sodium, the tablet, and inside you have hydrochloric acid. So we take the mass of this, it's 64.14. Now we take the tablet of sodium bicarbonate, put it into the acid, and we see the mass still same. Reaction has started. A gas is being formed which is filling this balloon up. Something new has formed. More reaction time takes place, more gas is formed, but you can see the mass does not change. Why is the mass not changing? Because it is following the law of conservation of mass, which says that the total mass of the reactants is equal to the total mass of the products. So during a chemical reaction in a closed system, total mass of the substance remains the same. According to the law of conservation, matter cannot be created or destroyed. In a chemical reaction, the total mass of the reactant equals the total mass of the products, because all atoms are simply rearranged to form new substances. Supposing you're asked to calculate the masses, so you have to remember that whatever is the mass of the substances reacting should be equal to the mass something formed. For example, here they said when hydrogen reacts with chlorine, what is reacting? Hydrogen and chlorine. Mass of hydrogen 18, mass of chlorine 633 has been given to you. How many grams of hydrochloric acid are formed? You know that mass of reactant should be equal to mass of product. What is the mass of hydrochloric acid? It should be equal to mass of hydrogen plus mass of chlorine. Mass of hydrogen 18 grams, mass of chlorine 633 grams. If you add these two, this is the mass of hydrochloric acid formed. Bismuth and fluorine react to form bismuth fluoride. If 417.96 grams of bismuth is reacting with 113.99, how many grams of, you will add it and that will be the amount of bismuth fluoride that is formed, based on the law of conservation of mass. This I just explained you. This is also based on the law of conservation of mass. I think you understand. When wood is burning, combustion is taking place. Combustion means burning, reaction with oxygen. Chemical change. Suppose you burn a large log in a fireplace until nothing is left. Small pile of ashes, smoke, heat, and light are given off, and the changes in the composition of the log confirm that a chemical change. You might think matter is lost, but no, it's not lost. It has changed into gases, other forms, and it is in the, so it will remain the same. The mass will be same. It has moved out. That's why we feel it is less. Oxygen has combined with it and it has formed this. So law of conservation of mass, mass is not gained or lost during a chemical change. This I already explained in this figure. Next question comes from structure of the atom, student book page 402 and 403. Here you have to compare between Bohr model and electron cloud model, which helps scientists to understand the behavior and difference between these two. You know what is Bohr's model? Bohr's model says that it shows electrons moving in fixed orbits or energy levels. So the electrons are moving in fixed energy levels around the nucleus. Helps explain electron energy changes when electron absorbs or releases. So electron can change energy. It can move from one orbit to another by either absorbing or releasing energy. But in electron cloud model, shows electrons are forming a cloud around the nucleus. It's not like energy levels. You cannot make out the energy. You just see an area in which the electrons are moving, where the density of the cloud represents the probability of finding an electron. It helps us understand that electrons do not have fixed path but are likely to be found in certain regions. It tells us that there is no, at one time you cannot tell where the electron is. So if you see, this is the electron cloud model. There is a nucleus and this area is where you can find the electrons. This is the electron cloud. Here there are different models of when the atom was being discovered. And so first model was made by Democritus in 400 BC, and he just said that it is atom is a solid particle. You cannot divide it. It is uncuttable. You cannot divide. Then in 1904, Thomson said it is like a choco pie. I say like a chocolate chip biscuit or a cookie dough. You have a positively charged ball, and there are negatively charged particles embedded in it, like chocolate chips. Then in 1911, Rutherford said that it has a positive charge which is in the center and the electrons are surrounding it. Then Bohr, this is the Bohr's model. So they've asked you between this and this. Bohr said that that the electrons, they could jump between orbits. They can go from one to another, but that would be either when they absorb or they release energy. And this is the electron. So you have to compare these two. So it says electron cloud model states that there is an area around the nucleus of an atom where the electrons can be found. Bohr model places electrons in fixed orbits around. This is the main difference. He's putting it in fixed orbits, and they said that it is in an area. Next question comes from Masses of Atoms, student book, page 405. How would changing the number of protons in an atom affect the element it represents? Interpret table 4 to identify the name and atomic number of an element. You know that the atomic number is always equal to the number of protons. Every element has a fixed number of protons. We cannot change. If the number of protons is changed, we will also change the element. So if there are 6 protons in carbon and we remove 1 proton and we make it 5 protons, then carbon, it will not remain carbon, it will change. So the number of protons in an atom is called its atomic number, and it is the identification of the element. It defines the element. If you change the number of protons, you change the atomic number. And if you change the atomic number, it does not remain the same element. Since the atomic number determines which element it is on the periodic table, changing the number of protons changes the element. For example, carbon has 6 protons. If it gains 1 proton, it becomes nitrogen. If it loses 1 proton, it becomes boron. So changing of protons will change the element. Here, this is a table where they've given you boron, the symbol, atomic number, proton. So you see, atomic number is equal to number of protons. And mass number is equal to the number of protons plus neutrons. This is called the mass number. Don't get confused between atomic mass and mass. Mass number is protons plus neutrons. 5 plus 6, 11. Carbon 6 plus 6, 12. Oxygen 8 plus 8, 16. Sodium 11 plus 12, 23. Copper 29. So this is the mass number. Mass number is equal to number of protons and number of neutrons, some of them. Atomic number is equal to only number of protons. Say, identify the element and the atomic number of the element with 29 protons. Now, which one has 29? This. If it has 29 protons, its atomic number would also be 29, and it will be copper. The number of protons in an atom's nucleus is equal to its atomic number. Atomic number of carbon is 6. Oxygen atomic number is 8. Therefore, if you are given any one of the following, either the name of the element, the number of protons, the atomic number, you can identify which of them is the particular element we are talking about. An element is made up of one type of atom. What determines the type of atom? In fact, the number of proton identifies the type of atom. Every carbon atom will have 6 protons. Any atom with 6 protons will be carbon. So what is mass number? It is the mass number is equal to number of protons plus number of neutrons. You can calculate mass number of copper. So if you know the number of protons and the number of neutrons, you know this is protons is 29, neutrons is 34. So you can add them, you'll get the mass number. If you know the atomic number of atom, you can calculate the number of neutrons in that. Supposing I give you the atomic number is 29 and mass number is 63. Can you calculate the number of neutrons? Yes. If atomic number is 29, it means it has 29 protons. If you know there are 29 protons and mass number is 63, subtract it and you'll get the number of neutrons. Next is mass of atoms. We are talking here about the chlorine atom has 17 and 18 neutrons. 8 protons, 10. Determine the atomic number and just calculation of that. It's the same as the previous one, where you have to tell how to calculate them. So if you know the atomic number of chlorine is 17 protons and 18 neutrons, what is the mass number? Mass number will be, add them, 35. Oxygen atom has 8 protons, 10 neutrons. What is its atomic number? Since 8 protons, atomic number will be 8. What is the mass number? 8 plus 10, 18. So mass number, proton plus neutron, and atomic number, only proton. Here, what is the atomic number? 17. Then masses of atoms, page 406. Now we talk about isotopes. What are isotopes? We are comparing two isotopes of carbon and how they are same and different. In this, they've given you the isotopes of boron. Now, when they write boron 10 and boron 11, this number 10 and 11 is actually the mass number. 10 and 11 is the mass number. Boron 10 mass number is 10. Boron 11 mass number is 11. They've already told you that it has 5 electrons. That means its atomic number is 5. 5 protons also. But in this case, if the mass number is 10 and 5 protons, what is the number of neutrons? 5. 10 minus 5. If it is 11 here, protons is 5. What is the number of neutrons? 6. Why? 11 minus 5. 6. So boron 10 and boron 11 are two isotopes of boron. They both are boron. They will have the same number of protons. That cannot change. So what is changing is the number of neutrons. So what are isotopes? They are atoms of the same element. They can have different mass number. For example, some carbon atoms have mass number 12. Others have mass number 14. Number of protons for each element will never change. So atoms mass number to differ, the number of neutrons change. So atoms of the same element that have different number of neutrons are called isotopes. To identify isotopes, scientists write the name of the element followed by the mass number. So we'll write carbon with mass number 12 is written carbon 12. Carbon 12 has 6 protons and 6 neutrons. Carbon 14 has 6 protons and 8 because 14 is the mass number. So to identify the isotopes, we write it like that. Here they've shown you the isotopes of carbon. Carbon 12, carbon 13, carbon 14. So carbon 12 has 6 protons, always 6 protons, 6 protons, 6, never change. Neutrons, electrons will also not change. Neutrons changes. Here you have 6, here you have 7. That's why 6 plus 7, 13. Here you have 8 plus 6, 14. So these are the isotopes of carbon. Number of electrons remains the same. Number of protons remains the same. Number of neutrons is different. And because neutrons is different, mass number is also different. Here chlorine. How many electrons does chlorine have? 17, 17. Protons, 17, 7. What is changing? Neutrons. 18 neutrons, 20 neutrons. Then we come to the last lesson, stability in bonding. What is the name of the element with symbol Na? This was updated. That's why the color of the slide is different, because this was updated later. First, they had just written what is the name of the element. Now they also added name the compound it forms when combined with chlorine. What is the name of the element chlorine? Name the compound. It's better try to memorize the symbols of these common elements. You can see the symbols are always written. They start with a capital letter. If there are two or letters in the symbol, the first one will be capital, the second one will be small. Capital. So when you see a capital letter, it is one element we are talking about. Aluminium Al, calcium Ca, carbon C, chlorine Cl, gold Au, hydrogen H, iron Fe, mercury Hg, nitrogen N, oxygen O, potassium K, sodium Na. We see some are different from the names because they are derived from Latin names. Stability in bonding, student book page 450 and 451. Here, the question was the element with symbol Na. What is it? It is sodium. Remember, Na is sodium. It comes from the Latin word natrium. Na is sodium. It forms sodium chloride. What compound is it forming with chlorine? It forms sodium chloride. When sodium combines with chlorine, it forms sodium chloride. Element with symbol Cl is chlorine, and it forms sodium chloride when it combines with sodium. What are compounds? The matter around you include elements copper, sulfur, oxygen, and they combine with other forms. When they're combining with other forms, they're forming, like chemically combining. The properties change, and then they form a compound. The copper in the here, this is copper, this is sulfur. They are different elements. Copper is different. It has different properties. But when they combine together, they are forming some greenish colored thing, which is known as copper sulfide. So copper sulfate isn't shiny and reddish brown like copper and sulfur, nor is it pale yellow solid like sulfur or a colorless, odorless gas like oxygen. And this is how it is formed. So copper sulfate is one of the compounds responsible for the blue-green patina seen on the Statue of Liberty. So this Statue of Liberty has this blue-green thing on it. This is because of its reaction with sulfur and oxygen. It includes copper, sulfur. It is very different from both the elements. So in compound, the elements, they lose their properties and a new substance is formed. New properties. A compound formed when elements combine often has properties that aren't anything like those of the individual element. Like potassium looks like this, iodine looks like this, it's a gas, but when they combine together, potassium iodide looks like this. So you see the properties have changed entirely. It is a compound formed from the element potassium and iodine. Potassium is shiny, soft, silvery metal. It reacts very fast, violently with water. Iodine is blue-black solid that turns to purple gas at room temperature. But the substance that it is a crystalline salt. Every element has a chemical symbol. For example, the chemical symbol Na represents the element sodium, and the symbol Cl represents the element chlorine. When we write NaCl, these symbols, this is showing that this substance has sodium and chlorine. It's sodium chloride. So this is called the chemical formula of sodium chloride. These are symbols and this is chemical formula. Elements and compounds contain exact number of atoms of each element. Then says explain how the electron configuration of neon makes it unreactive. Explain why some elements are stable on their own while others are more stable in compound. Now, we have to understand this, that when a chemical bond is formed, there is a particular, all atoms, they want to become stable. And how they become stable is when they acquire a filled in outer energy level. So it should have 8 electrons in its outermost energy level if it is not the first energy level. In the first, maximum is 2, but in the second or third or fourth or fifth, it should be 8. So if it is not 8, it is unstable. And then the element wants to be stable, so it will react with that substance. The noble gases like neon, helium, krypton, xenon, they are noble gases. They're called noble gases. They belong to group 18 and they don't react. They are unreactive. Very rarely they will react. Unreactive. Why? Because they have a complete outermost energy level. First compound containing a noble gas was not made until 19. Atoms of noble gases are unusually stable. They are very, very stable. Why? Because of their arrangement of electrons. Let's come to that. Here you see this is the electron dot diagram. You can recall from your class that electron dot diagram shows only the electrons that are present in the valence electrons or in the outermost energy level. These are the valence electrons, outermost energy level. First energy level can have maximum 2. So helium has 2. It does not need any. So it is stable. Neon has 2 energy levels. The second energy level has 8. It's full. It does not need any electron. So it's stable. Argon also has 8. Krypton also has 8. Xenon also. So all have complete energy levels. That's why they are stable and they are not reactive. So this is a unique property of noble gases. They are unreactive. An atom is chemically stable when its outer energy level is complete. Outer energy level is complete. And when is it complete? When it has 8 electrons here. We're not talking about the first right now. If it has 8 electrons in the outermost energy level, it is complete. The outer energy levels of helium and hydrogen are stable with 2 electrons because it's the first energy level, maximum 2. So hydrogen and helium will be stable only when they have 2. Helium already has 2, so it's stable. Hydrogen needs 1. The outer energy levels of nearly all other elements are stable with 8. So when they have 8, they are stable. The noble gases are stable because they have a full outer energy level. Here it shows the electron dot diagram of the other elements. Here you can see lithium has 1, so it is unstable. Sodium has 1, outermost, last one, 1 electron, so it is unstable. Beryllium has 2, unstable. It is in group 2. In group 3, there will be 3. In group 13, 3. In group 14, 4. In group 15, 5. In group 16, 6. So this is how the energy levels will decide whether it is going to be the valence electron. Valence electrons are the electrons present in the outermost energy level. So valence electron will decide whether it is going to be stable or not, whether it is going to be reactive or unreactive. Explain why some elements are stable on their own while others are more stable in compound. If an element has a full outer energy level, it has a tendency to not react because it is already stable. If an element does not have a full outer energy level, then it will form a compound by gaining, losing, or sharing electrons with other atoms in order to achieve full outer energy level. So this is why they are stable on their own. And if they are not stable, they form compounds. So if you ask why they form compounds, because of their incomplete energy level. The label on a box of cleanser states that it contains CH3COH. What elements are now? What are elements are there? There is C, carbon. There is H, hydrogen. There is another C, carbon, O, oxygen, and H. How many atoms of elements? So if you can count. How many atoms of carbon? 1 and 1. 2 atoms of carbon. How many hydrogen? 3 and 1. 4. Oxygen, 2. You can count the number of letters. That means that many atoms are formed. So students, that's all that's coming for your multiple choice questions in your end of term exam, which is scheduled on the 20th of November. That's a Thursday. I wish you good luck for all your exams, especially for your science. And I hope you'll be amazing. You'll do wonderful. Please keep in mind the things which I told you, and inshallah, you're going to do well. Good luck.